Hello again, this is Harry Lythall, SM0VPO. Now this video is a follow-up to my recharging e-cigarettes video, but today I will show you how to reuse the vape cells to power radios and other electronic equipment, and also how you can safely charge banks of cells without the need for a special balancing charger unit. If you want to replace cells, for example in an old radio, then you would need to add more connections to the radio to access each individual cell. And in this video I will give you some diagrams that you may wish to download. The easiest way is to pause the video and gently hit the control and the print screen button, and then you can paste the picture into a drawing program such as MS Paint, PSP or even Photoshop. Before I go into the details, here is a bit of useful information. When you are playing with power units and LiPo cells, you may like to use these dirt cheap alligator clip jumper wires. They cost about $2 for a bag of 10, and they're about 400mm long each, but they're such bad quality that they can be of use. They're so cheap and they've cut manufacturing costs that they can't take any current. I'll show you. I set my power unit to 1 ampere and short it with one of these leads. You see, there is over 1 volt drop across the cable at 1 ampere, so each cable has got a resistance of about 1 ohm, and this tells me that they're not made of copper wire. A magnet will stick to them. This is showing that they are ultra cheap iron conductors, no copper in there at all. With 2 of these cables you have 2 ohms, so a direct short through these wires will not cause a LiPo cell to explode. So the bad quality cable will protect the cell. Now LiPo cells are genuine rechargeable cells and have a capacity from 350 milliamp hours to about 850, but the most of them are around about 550, and they are designed to deliver a couple of amperes to a power heating element, so they will deliver about 5 times the capacity in current. Now these 5C cells will therefore power RC models such as small helicopters and aeroplane glider motors. I use 3 cells to run my old FT290. Note that you need to be careful not to allow these cells to be shorted, otherwise they can get hot and even possibly explode. The thin wires used in a vape also act as a fuse to prevent an explosion, possibly blowing out your teeth or something equally nasty. But having said that, I've never seen one of these cells explode myself. Now these LiPo cells have got a nominal terminal voltage of 3.7 volts, but the actual voltage range is from 3.5 volts when they're discharged, rising to 4.2 volts when they're fully charged. And you can connect them in parallel to get a greater capacity without using a special circuit. Then you just treat them as a single cell. You do not need a charge balancing circuit if they are connected in parallel. These voltages are different for different cell technologies, so you should check on your cell's specification. As a general rule, here are 4 different technologies. A simple LiPo charger circuit can be to connect 1 cell at a time to a laboratory power unit set to 4.2 volts with a current limiter set to C/10. Now these e-cigarette cells, however, will comfortably take 300 milliamps or more depending upon the cell capacity. You can charge these particular e-cigarette cells with a higher current, but 300 milliamps is kinder to the cell and it preserves the life of the cell. But for cells designed for lower discharge current, you should charge at C/10 or 1/10 of the battery capacity. So let us charge our 550 milliamp hour e-cigarette cells. My power unit has two indicators that are of interest. CC, which is constant current, and CV, which is constant voltage. For my LiPo cells, set the voltage to 4.2 volts, set the current to 300 milliamps. Now when you connect the LiPo cell, the power unit will immediately go into current limiting. The CC lamp will light and the power unit turns down the charging voltage to maintain the maximum current allowed, which in this case is 300 milliamps. Now as the cell charges, the current will not exceed 300 milliamps, but the charging voltage will slowly rise up to 4.2 volts. When 4.2 volts has been reached, the constant voltage limit will kick in, the indicator will change, and the cell itself will draw less and less current until eventually it falls to a very low figure, typically 10 milliamps or so. Now with these values, a 550 milliamp cell will take about 1.5 hours to charge. You do not have to wait until it reaches 10 milliamps. At 4.2 volts you can consider the cell fully charged, but I usually wait for it to get below about 55 milliamps for a 550 milliamp hour cell. If you don't have a lab power supply like mine, then you can use a USB mobile phone charger or even the USB outlet from your personal computer. All you need to do is to add a silicon diode in series with the cell to reduce the USB 5 volts to 4.25 volts. You also need to add a low value resistor to restrict the current. You should monitor the charging voltage so that you know when the cell is charged. Cells can practically be left on charge for many hours using this technique, but 24/7 float charging of LiPo, nickel metal hydride and NiCad cells is not to be recommended, since the cell maximum voltage can vary a little with excessive temperatures. Lead acid cells, however, can be float charged indefinitely, providing the terminal voltage never exceeds 2.3 volts across any one cell. Now I'll go a little further with wiring the cells in series. Now it is series connected cells that need charge balancing circuits. The reason for this is that the charging voltage should never be allowed to exceed 4.3 volts or the cell can break down and possibly explode. In my experience, nickel metal hydride cells are also sensitive, but many manufacturers often ignore this. Now if you look at this diagram, I shall explain why. Here are 3 LiPo cells connected in series. We know they all have a terminal voltage of 4.2 volts when fully charged, so we would need to have at least 12.6 volts available, with a current limiting set to 300 milliamps. Unfortunately, no two cells have the same physical capacity. They may vary a little bit with age, with temperature, or even from one manufacturer to another. So the cell with the lowest capacity will become charged first, just as in the cell to the right of the screen. The cell to the left of the screen has the next highest capacity, and the cell in the middle has the highest capacity. The cell in the middle with the highest capacity will take longer to charge because they're all connected in series. They are all charged at the same current. So if we are to prevent cell number 3, the weakest cell, from overcharging, then we need to restrict the voltage across that cell. In fact, all cells should be protected in exactly the same way. How many times have you bought a cheap imported battery powered electric drill like this one, only to find that after a few battery cycles you have to buy a new battery? Some of them are still supplied with a 12-volt battery pack using 10 1.25 volt NiCad or nickel metal hydride cells, and they fail for exactly the same reason. If you're going to connect 2 or more cells in series, then you need to prevent them from overvoltage. One way to do this is to connect across each cell a voltage restrictor, a clamp or a current shunt, whatever you want to call it. In this way, when a weaker cell reaches 4.2 volts, the shunt will bypass the charging current, allowing the other cells to reach their full charge without destroying the weaker cell. I just ripped all the cells out of my battery and I used an external 12 volt lead acid battery. I get a lot more torque. 12 volt lead acid batteries are by far more tolerant to heavy discharges, and they tolerate 24/7 float charging at 13.8 volts. Now, for charging a string of series connected cells, a simple voltage clamp can be made with just two general purpose switching transistors, for example BC547 or 2N2222, as long as they can handle the bypass current. R1, R2 and R3, they form a voltage divider that turns on the transistors if the voltage exceeds 4.2 volts. Now R3 has been added so you can select it to give exactly 4.2 volts. One of these across each cell and your battery bank will be protected and can be charged normally. But there is a more simple method. If all the cells in a battery pack are rewired and connected in parallel, then the weaker cells will simply draw less charging current and all the cells will have the same voltage balanced. The battery is fully charged when all cells reach 4.2 volts. Now this is much easier and it's a perfectly safe method without a balancing circuit. My studio microphone here uses two cells to power an operation amplifier with 7.4 volts, so I chose a power on-off switch that has two poles and can switch each pole in two directions. Now this is sold as a two-pole two-way or double pole double throw switch. I wired the second cell so that when the switch is on, the two cells are connected in series to give me 7.4 volts to the amplifier. But when the switch is off, the two cells are rewired in parallel and the two cells can be charged simultaneously with a 4.2 volt charger. In this project I have used the microphone ground lead as the negative charge terminal and the plus 4.2 volt charger terminal I connected to the metal potentiometer chassis. Now I can charge the batteries without adding external wires to the amplifier. Now let us imagine that I have a radio that requires 2, 3 or more cells. In my FT290 I had 3 LiPo cells to give me 12 volts. The first cell's okay, but I added a cheap 5 volt relay to each of the other 2 cells, as in this drawing. When the relays are not energized, the cells are all connected in series and I have a 12 volt battery pack. As soon as I connect a 5 volt battery charger, the 2 relays energize and the contacts change over and all 3 cells are wired in parallel. Now I use the constant voltage charging and I do not need a charge balancing circuit at all. I can also charge my radio, my studio microphone and all other equipment with the same charger. Now these relays are sold on eBay for about $1 each, so they're really cheap. Now today I use 3500 mAh nickel metal hydride cells designed for mobile phones to power my FT290. These relays normally draw about 40 milliamps each, so you could alternatively just measure the battery voltage and charging is complete when the combined cell voltage reaches 4.2 volts or the charging current stops falling. So there you have it, how to charge rechargeable cells safely without a LiPo charge balancing unit. So I want to thank you for watching and I hope you found this video interesting. I hope to see you again in the next video, but don't forget to click on some of these buttons below and feel free to leave comments. All constructive comments are gratefully received. So I wish you very best regards and have a nice day from myself, Harry Lythall, SM0 VPO, an Englishman in Sweden.